Hello, thanks for joining. My name is Muhammad Farzanullah and I'm a master's student at McGill University. Today I will be presenting our paper which has been accepted for presentation at the 2022 Vehicular Technology Conference. The title of the paper is Multi-Agent Reinforcement Learning for Channel Assignment and Power Allocation in Platoon-based CV2X System. So this would be the outline of our presentation. We would first start with introduction. This would be followed by the system model and problem formulation. Next, we are going to discuss the reinforcement learning based resource allocation. Then we are going to show the results and finally we are going to conclude our presentation. So starting with the introduction, the cellular vehicle to everything or CV2X is a vehicular communication paradigm via cellular networks. It is a promising solution to reduce traffic congestion and road incidents in future smart cities by enabling the cooperation among connected and autonomous vehicles. Typically, a CV2X system includes vehicle to network or V2N and vehicle to vehicle or V2V transmission. The V2N transmission connects the vehicle to base station, while the V2V transmission provides direct information exchange among the vehicles in proximity. To enable efficient C-V2X operation, emerging cellular systems must provide high data rate connectivity to vehicular users of V2N links for gaming and video streaming, together with V2V services that require message exchange among vehicles with high reliability and extremely low latency. Satisfying such requirements and challenging and hence calls for an intelligent resource allocation design. So moving on to the motivations, there are a few characteristics of the CV2X systems which makes the problem challenging. Firstly, the channel variations are fast because of the high vehicular mobility. Secondly, the V2N links require a high sum rate, while also the V2V links require extremely low latency and high reliability. Due to these stringent requirements, an intelligent resource allocation design is required. So, as far as the current approaches are concerned, there are certain limitations. So, for example, the centralized optimization results in higher channel state information overhead. And secondly, the traditional distributed optimization cannot solve hard to model problems. So our proposed approach is the multi-agent reinforcement learning for resource allocation design. And we were able to show that we achieve a close performance to that of the centralized exhaustive search algorithm. Moving on to the system model and problem formulation. So this figure shows our system model, which consists of a single cell setting. In this system model, there are multiple V2N users, which are depicted as black vehicles in the diagram. All the V2N users transmit at a constant power. Also, the V2N users in the uplink have pre-assigned orthogonal spectrum subbands. Meanwhile, the V2V communication occurs when the platoon leader periodically transmits the safety message to all platoon members. So in this figure, the red vehicles are the platoon leaders, while the blue vehicles are the platoon members. And so the platoon leaders in our system model, the platoon leaders reuse the subbands assigned for the V2N users. So the goal is to find for each of the platoon leader the V2N subband it selects along with the transmit power. So moving on to the achievable rate for the V2N links, the first formula shows the SINR, the signal to interference plus noise ratio for a V2N link. So for each V2N uplink, the source of interference would be from the uh, platoon leaders that are using the same subband to transmit. And so using this SINR, we can write down the achievable rate for each of the V2N link using the Shannon capacity formula. Moving on to the achievable rate for V2V links. So for the V2V links, there would be two sources of interference. Firstly, there would be interference from the V2N users. And secondly, the interference would be from the other Platoon users that are using the same subband. And so as before, we can use the SINR formula to write down the uh, rate using the Shannon capacity formula. So moving on to the problem formulation. So our goal is to simultaneously maximize the achievable sum rate of V2N links and the reliability of each V2V link under a latency constraint. So for the V2N links, the achievable sum rate is given by the sum of the rate of all the V2N users. Meanwhile, the for V2V links, the reliability is given as the successful delivery of packet having a size t within the time constraint t, and it is given in the formula depicted in red. And so in this scenario, we aim to find the joint channel assignment and power allocation scheme at the V2V platoon leaders that is simultaneously going to maximize the two objectives. And so for this, we use the multi-agent reinforcement learning. So moving on to reinforcement learning based resource allocation. So in our approach, each platoon leader acts as an agent and interacts with the unknown environment. Based on the reward it receives, it refines its strategy for power allocation and subband allocation. In order to ensure collaboration, we use a common reward for all of the agents during the centralized training stage. Moreover, the testing is implemented in a distributed manner where the trained deep Q network is used to select the action. So there are three main elements in a reinforcement learning problem, which are the state space, action space, and reward design. So moving on to the state space design, it consists of the measurements from the last time step for each of the agent. And so the state space consists of the direct channel of the leader to the platoon members. Also, the state space consists of the interfering channel from other platoon leaders as well as the B2N user. And it also includes the remaining payload and remaining time limitation after the current time step. Meanwhile, the action space consists of the combination of occupied subband and transmit power level. So to design the reward, uh, like it is a multi-objective problem where we need to maximize the uh, probability of V2V delivery probability of V2V links and sum rate for V2N links. So our reward is consists of three parts. The first part shows the sum rate of all the V2N users. The second part shows the sum rate of all V2V links. However, for this case, we give it a value of uh, U if the transmission has been completed. And so this is to indicate to the algorithm that the transmission is complete and like to show that it has successfully completed the transmission. The third part consists of the uh, like it is all consist of the increasing price as the transmission time of the V2V link grows, and it is basically there to indicate to the like for the algorithm to complete the V2B transmission as soon as possible. So moving on, the reinforcement learning algorithm we use is the deep Q learning. In reinforcement learning, the goal of the agent is to maximize the cumulative return, which is the sum of the reward at the current and future time steps. Meanwhile, a policy is the function that maps the state to actions. The Q value gives the expected return of a state action pair with a given policy. And so the aim is to find the policy that maximizes the return at each time step. So in Q learning, if you can accurately estimate the Q values, the optimal policy would be to take the action in each state that maximizes the Q value. And in deep Q learning, we use a neural network as a function approximator for the Q values. The deep Q network consists of a neural network which takes the state as the input and outputs the Q value of each action. Moving on to the training and testing algorithm. So we consider an episodic setting where each episode corresponds to the time limit of delivering the V2V path. Each episode consists of multiple time steps. At the start of each episode, the vehicle location and large-scale feeding is updated, while at each time step, the small-scale feeding is updated. At each time step, each of the agent observes its local channel and takes an action. Based on this, it receives a reward and moves on to the subsequent state. This state action reward state tuple is stored in memory and it is used to train the deep neural network. During the testing stage, each agent collects a local CSI, and based on that, it uses the trained neural network to select the optimal action. So moving on to the illustrative results. So we consider a single cell urban scenario setting as given in the TR36.885 of 3GPP. The TR provides the vehicle speed, drop models, direction of movement, as well as the V2N and V2V channel model, including path loss and shadowing. The small scale fitting is modeled as Rayleigh fitting, and in our case, each V2V platoon consists of one leader and three members. Also, we set the latency T as 10 milliseconds. Moving on to the simulation parameters. So some of the important simulation parameters are that we vary the number of V2N users between 1 and 2. There are 4 V2V platoons. Also, the transmit power of each V2N user is fixed at 23 dBm, while the transmission power of the V2V platoon leader is discretized into 4 levels, which is 23, 10, 5, and minus 100 dBm. We train our algorithm for 2000 episodes, and for testing, we use 100 episodes. So moving on to the results, we compare our algorithm with the centralized exhaustive search algorithm. The centralized exhaustive search algorithm exhaustively searches for all subbands and power levels for each user's each time step that maximizes the rate. And the second benchmark is the random allocation, which randomly selects the subband and power level at each time step. So over here, we show the average rate of V2N links against the payload size B of the V2V link. And so it can be seen that increasing the payload size decreases the performance or decreases the average rate of V2N links. And this is because when we increase the payload size, the V2V link would require higher time to complete its transmission, and so there would be greater interference to the V2N links. Moreover, we can see that the average V2N rate is greater with a larger number of users, since with two available subbands, the interference from the V2V link reduces. Secondly, we show the average payload delivery probability against the payload size B. And over here, we can see that similarly, the performance decreases as we increase the payload size B. Also, it can be seen that the payload delivery probability is greater for two V2N users, and this is because we have, in this case, we have more subbands. So, for in that case, the interference amongst each other decreases, and due to which the performance is greater. So, moving on to the conclusion. So we use reinforcement learning approach for distributed resource allocation in platoon-based CV2F system, where multiple vehicle-to-vehicle platoons were allowed to reuse the spectrum of vehicle-to-network transmissions. The proposed method was decentralized, and the global channel information were not required for the agents to make the decisions. And so using this, we were able to achieve high V2N rate along with the high V2V payload delivery probability. And the results achieved were close to that of the centralized exhaustive search algorithm. So thank you for listening to the presentation. Have a nice day. Bye.